I'm talking about IDDQ. This is the fourth test in the series of which I'm showing, going through how the Trillium tester I worked on for 13 years did testing. I've pulled IDDQ because it's a well-known test, and it's an example of a parametric test. I'm not going to go into all the parametric tests. They're all roughly the same. When I speak about IDDQ or IPD, I know it's the same test. So IDDQ specifically speaks about the steady state current, a steady state current, or the quiescent current. In the top corner, one can see a very simple CMOS inverter. Okay, the CMOS inverter, your top FET is your P channel, your bottom FET is your N channel. Now, when one has a logic input 0 or 1, only one of the transistors will be conductive at that point in time. Either the top or the bottom. Either the top or the bottom transistor. When you've got only one transistor active, your other transistor is blocking. You're not meant to see any current flowing from VDD to VSS. This is what one can call static current. Static current is when the device is not switching. The device is not being clocked, it's not being switched. The device is totally static. Okay, the advantages of IDDQ is one can measure the effects of the process, and you can find some defects which would go by and would be functional, sort of a burn-in test, because you're able to detect leaky transistors which would have failed when they got out into the field. Okay, it's a simple test. I'm explaining in the next few slides how it is done. Okay, we start off with our device powered down. Step 1 is I close the device relay, the driver relay. What I've done is I've closed the driver relay. I've connected the pin out, the tester's outputs to the input of the device under test. Okay, that's done. I am now powering up the the chip, giving the chip power using the device power supply. The tester I worked at had two types of powering the chip. The device power supply was a higher current device. It was able to provide higher current than the PMU. So you're powering up your device, and you are going to start wiggling your inputs. You're going to start wiggling your inputs, and you're going to clock the device, and you're going to run a pattern. When the pattern stops, your device is going to be in a known state. In a known state means that I'm in a state which is known. Obviously, that I'm putting the device in a known state, I'm not going to use very strict timing, and I'm not going to use very strict logic levels. I just want to put the device into a known level. Okay. the device is now in a known state. What I'm going to do now is first to connect the PMU. Connect the PMU at the same voltage as the power supply. They're all calibrated to the same voltage. You're not going to have current flow between the PMU and the PSU. I'm then going to disconnect the PSU. The current, because the device is at a known low current state, is minimal, very little. Okay, once I've connected the PMU, I'm going to disconnect the driver relay on all non-essential pins. All non-essential pins, I'm going to disconnect the driver relay. Why am I disconnecting the driver relay on non-essential pins? Because I don't want to measure leakage current going through the tester to the pins. I want the pins to be in the air so that I don't measure leakage through the tester. Okay, so I have all my pins, non-essential pins. What do I mean by non-essential pins? For example, I don't want to leave reset in the air. I need to know that the pin like reset needs to be at a known value, so I can't disconnect an essential pin. There are some pins which need to be left. Okay, at this point in time, I institute a current measurement, and I measure the current, which is a steady state current of the device at a known state with its inputs, most of its inputs open tri-stated in the air. Okay. The previous test I explained was functional test. A functional test that either is a go or no go. Either the pattern will pass or the pattern will fail. There's no gray area in a functional test. Okay, there's no gray area. Either you're passing or you're failing. You can't make it pass. The output of this is an analog value. It's going to say to you, I'm measuring 100 nanoamps, 100 milliamps. It's giving me an analog output. Now, the analog output, I decide whether that is acceptable or not acceptable. And that is where it would be something called a test limit. I'm now opening up something called dynamic test limits, which was something which was done at the factory I worked at, and I'm going to show you what it was, and I'm going to explain to you the shortfalls of dynamic test limit. Let's assume that one wants to find the highest or the higher than average IPD. I'm using IPD, not IDDQ, because it was an IPD test which I'm talking about. on a particular wafer. As all the wafers go through the same manufacturing process, some will have more, some will have less current. But what I want to measure is I want to measure the ones and pull out the ones which are outliers. Okay, so what was decided to be done was at the end of, shall we say, it started off that they would measure the first 4 or 5 dies with a fixed limit, and then the limit would go up or down based on the previous test results. Okay, so what would happen is if you have 10 dies down the line, then you're going to measure this die with respect to the 10 dies on each side of it. The 10 previous dies. You don't know the next dies, but you are going along and you are using this to move it up and down your current limit, so that you're finding the dies which are exceptionally high compared to the rest of the dies in the wafer. Okay. This was done and it increased the yield no end. Okay, everyone got a pat on their back. Kol hakavod. Well done. You've increased the yield 100%. 100% value. Okay. In the second part of 2003, somewhere around 2003, I